I'll introduce you, and then you can just get started then. So just give me one moment.
You got it.
All right, can folks hear us okay on YouTube? Okay, I think I see folks. Hello. Okay, beautiful. Folks can hear us. Okay, I guess we could get started. Yeah, so welcome everyone to lecture 51 of GPU Mode. Today I'm really thrilled to introduce Jake Cannell, who is the CEO of Vast AI. Jake and I met a while back, specifically as I'd been getting really interested in consumer GPU performance and figuring out why they're not more used in actual deployments. And turns out Jake has been sort of thinking about these problems for a long time. He's basically been scale built a long time ago. And so I think he's going to give us sort of a nice journey of how he basically the evolution of GPUs and how he came to basically the conclusion that something like Vast must exist. So yeah, without further ado, Jake, thank you for coming.
Thanks for the intro, Mark. So this talk is going to cover a number of different things. It's sort of my personal journey working with GPUs for a long time and what led me to where I am today. And along the way, a lot of it will be about CUDA. I know this is CUDA mode, but I'm going to start a little bit before even CUDA. So I was born in 1978 when the Atari home console just, I think, came out then. One of my first memories was playing that game system. Really staying up all night and playing with my dad and my brother. And I grew up during the video game revolution. So every couple of years, new games would come out and the graphics would be more advanced. And it was this I didn't even know it was called Moore's Law then, but it made Moore's Law very visceral. When I learned about what that was, the progress in games was evident, obvious, and extremely important to my life and my trajectory. I knew I wanted to work in games from a really early age. So I cited some highlights here that were meaningful and important to me. I remember when Doom first came out, I was in high school and I saw it running on this machine, this cluster of network machines that were playing Doom multiplayer in a shopping mall. And I thought it was running on a supercomputer or something. So I'd never seen a 3D game that was that fast and dynamic, that level of rendering quality, which I know sounds ridiculous today for many of you who grew up later. But really, graphics used to be a lot worse, and they've gotten tremendously better over time. And I've also thrown in one of my own. This is my own project. So I started programming, writing very simple games in Quick Basics. That's literally all I had in Missoula, Montana, in the dark era before the internet. And I went to college at UCSB. I got access to the library. I started devouring graphics books, and I then really got into graphics programming, especially after following the journey of developers like Carmack working on games like Doom, and really wanted to understand in great detail how all of that worked so I could recreate it myself. And I've thrown some more, even though I've been out of games for a bit. I've thrown a bit more of the evolution, like Crisis in 2007, where one of the first games to have really achieved photorealism in a lot of different types of scenes, and now to the modern day, where I'd say the Unreal Engine 5 has mostly solved graphics. For all intents and purposes, it's mostly now a problem of art production, cost, and quality. All right, and at the same time, I also became interested in transhumanism, and I picked up this book from Moravec, I think it was Mind Children, and he was one of the first to make this argument that the progression of Moore's Law would inevitably lead to AI, and that also profoundly influenced me. On the left is also a very interesting, I recommend checking out Modeling the Human Trajectory. Makes an interesting argument of fitting GDP growth. What's the simple fit GDP growth in a Bayesian sense? And it's a hyper-exponential function in the sense that GDP doubles 20 years, then it doubles 10 years, and so on. The rate of doubling itself is increasing exponentially. All right, so into graphics. My first serious project in graphics was quad tree fractal planetary terrain. What does that mean? I was very interested in this idea of creating planets and a video game where you could be out in space, you journey down to planets, and it would actually procedurally generate the entirety of the planet. And this was just barely possible. In some sense, I think Elite had pioneered an earlier version of this, a much more primitive graphics, but I wanted to achieve like really high quality. And I was working with the GeForce 256, which had just, I got one up not too long after it came out, and it had this new capability for that time. It was one of the first GPUs where they had an actual hardware processing of the entire transform engine. So the CPU could hand off all of the triangles and geometry and have that all handled in the GPU. This is long before programmability, long before CUDA and all that. And at this time, the earlier generation of cards, the first generation, like the Riva TNT, which I had, they were mostly just rasterizers. They were handling just rasterization, texture lookups, and whatnot. They weren't even really fully programmable. So this is a screenshot of my demo, which I became somewhat locally famous for, this planetary zoom terrain engine thing with these procedurally generated terrains. And I got in touch with, through my roommates and people that worked at this Meta Creations, and he put me in touch with this guy, Musgrave. And Ken Musgrave was actually wrote the book, one of the books that I'd read at the library called Procedural Graphics. And I ended up using some of this tech as the real-time viewer for their project Mojo World. I don't want to talk about this too much. This is before the CUDA days, but I was using, the principal technique here is use quad trees, and then you expand the quad trees dynamically based on the viewer perspective. And so you can take advantage of the projective transform such that things that are really close to you need higher detail than those in the distance. And you can get it really down to, you only need about as many triangles as there are pixels. All right. Also don't want to go into this too much, but I was really, at this time, spending a lot of time thinking about how to procedurally generate complex, realistic patterns such as terrains. One of the techniques is multi-scale noise fractals. Noise itself, in those days, was something you run on the CPU, was kind of expensive. And so I developed this technique to cache the lower frequency noise levels and interpolate them so that I didn't have to generate 32 levels of noise for a planetary sized terrain. I could only have to generate the current highest frequency level, and the rest I could interpolate from previous cache levels in the quad tree. And that enabled this to actually run in real time. And then there's more advanced techniques like multiplicative noise, which has an example here, which I think is there's an interesting relation to neural networks later, that you can think of neural networks as the weights as being a two-dimensional space. And a little work later on how you would use that, some of the techniques from quad tree terrain and fractals as a prior on neural networks. Because experience working with these for a long time, you eventually get, you realize that a lot of patterns in nature there's a first level approximation you can use with taking advantage of faking the higher frequency details of the wavelets and using a fractal. In some sense, it doesn't exactly matter that you exactly capture all the details. It matters more that you capture the properties of the distribution. And so that's why fractal terrain, it's relatively easy to get something that looks reasonably good, because the exact details of where all the high frequencies are and the exact shapes are sort of arbitrary, in that they are this result of random decisions made by geology a long time ago. And they don't have sort of innate complex structure. They have random structure. All right, and then in college and after, for a while, I was working on a video game for a long time. I don't want to talk about this too much, but this influenced a lot of my later views on algorithms and how I approach neural networks. And one of the main problems you run into in games is just there's this enormous amount of complexity of simulating everything in the world. And I really began to appreciate the ideal or the allure of more simplified algorithms that had great generality, the ability to model or simulate a wide variety of phenomena with a smaller set of code. And then after my game company did not work out, this game Chain of Command did not actually advance past like a playable alpha or beta. I went to work at Pandemic, which is acquired by Electronic Arts, and I ended up making a much better, more impressive version of my train engine. And this time now, the GPUs advanced. The Xbox 360 was one of the few times I think that ATI had a much better GPU than NVIDIA. And Microsoft had an amazing debugger, had this made development much easier and much more like a smooth experience. But the main thing that was really impressed about this GPU is it could pump out a couple triangles per clock, which meant that it had enough performance that I could tessellate triangles down to the level of pixels. And so I do this like thing where you like look at the press a hotkey in my demo, and you'd be switching to wireframe mode, and sometimes you wouldn't quite tell the difference between wireframe mode and non-wireframe mode. That's because it just turns out that when the triangles are tessellated down to pixel level, there's not that much difference in the display. And it had atmosphere. This is actually not a shot from that actual demo, but it's very similar. This is some later thing I found online, but it's very, very similar to what mine looked like. Okay. I think I'm about done with terrain, but I did spend 5 years of my life on it, so it did influence a lot of my later views on neural networks. And some of these same algorithms I was able to apply, as we'll see, in my later work. So the really interesting thing about terrain work that I think the main lesson that I learned is you can think of this is almost like an AI problem. I have this tree adaptive data structure. In this case, it's a quad tree representing the surface of a planet. And I need to make these decisions around which nodes to expand and when. And you can think of it as sort of like a decision problem where it's a cost-benefit analysis, that I have the cost of every little patch is fixed, it's a constant. It's the cost of rendering those triangles. But the benefit varies dramatically. And you can think of the benefit as being, or the utility as being driven by reducing approximation error. And there is some idealized image. There's always, everything is an approximation, everything. And so there's an idealized image, which is the image that you could render if you had far more time or more compute. And you can measure the approximation error from that ideal image to what you can achieve with your current triangle budget. That's your utility function. And so from that cost-benefit analysis, you can derive a few things. And one of the interesting ones is that there's sort of an economic equilibrium, that any really efficient allocation, a Pareto-efficient allocation, will result in an economic equilibrium where the price is roughly equalized. What do I mean by that? I mean that large triangles have a higher approximation error. So there is a large amount of utility in subdividing a large triangle and replacing it with subdividing it in half and quadrupling the number of triangles used to represent that patch of the surface. And so after you apply this optimization, if you've done it correctly, you result in all triangles having roughly the same, roughly comparable screen size in pixels, and getting down, say, roughly the two pixel size triangles. And that's all done in screen space because it's the error of our utility function is measured in screen space. So in some sense, you can think of this as a real-time AI optimization problem where I'm trying to optimize the utility function. All right. And then by 2009, 2008, 2009-ish, CUDA had launched in 2008. It's really hard to express how meaningful CUDA was to, like, from the perspective of a graphics program. It was a major, major advance. Before this, you're just doing all this stupid stuff. Like when I was generating these terrain patches, I had to generate geometry and texture, and I'd run a bunch of procedural algorithms. And you had to literally render triangles just to basically like run your algorithm over the output, a loop over an output array. You had to actually render a triangle. You had to make sure that all of the geometry match and the texture coordinates were not out of whack, so that the pixel engine could actually like invoke the pixel shader to run your code on the correct outputs. CUDA was just a breeze to work with. It was so much easier. It was C++. There was templates. Templates were a game changer because now you could actually have large amounts of reusable code and specialize it for different things that you're doing. So it was a huge advance. And at this point in time, I'm moving beyond quad trees. Like the really cool, interesting thing now to do, like the future of graphics, and pretty clear to me, would be using some of the same techniques, but now extending them to the third dimension so that you can model the entirety of the scene, all the complexity of the scene in one standardized data structure of voxels that then we can comb trace or ray trace through. And the particular variant of this I was using was based on signed distance fields. And so the idea of a signed distance field is that you're representing in space the distance to the nearest surface. And I had a few little clever tricks with this that I was also like using sub bits of that to represent alpha transparency.
Jake, just sorry to interrupt you, because your mic sort of sound dropped off like quite severely.
Can you hear me now?
Yeah, people in chat, by the way, do have the feedback that it is echoing a bit. So I don't know if like maybe you can quickly click on settings and then go to
I'm
audio.
sorry. I should have really tried this earlier, but
Yeah, maybe click reduce background noise.
let's
Okay,
try
maybe
that.
talk.
How's that?
It's
Is that better?
chat. Is this better? I think it is. Yes, actually, it's clear.
Do I need to move this a little bit away? Does that help?
This is significantly better now. Yes, I think this is
Okay.
good.
Maybe I'll also try to talk slower as soon as I start to speed up a little bit.
I think it's actually perfect now. I don't hear any echo. It's perfect. Let's go. Yeah.
Cool.
People are happy.
So there's a lot. I can go into a lot of detail with this. I'm not going to go too much. I don't have a huge amount of time. But the other interesting thing about working with data structures like this is that it's a highly irregular algorithm. And this image somewhat illustrates it. This image is basically the number of op-tree cells that were visited along that ray. And so you can see in the areas that it's white there because the ray was glancing along a surface for a long period of time. So it's going through many different transitions, navigating through many different levels of the op-tree. Whereas it's dark where the ray aims to sort of encounter the surface relatively early on, and that surface was mostly aligned to the direction of the ray. And around this time, I got somewhat scooped by this paper, Gigavoxels, which used related techniques, but they were mostly, and I think really well illustrated some of the potential of voxels. You could do clouds, you could do detailed geometry with great anti-aliasing. It sort of integrates everything, foliage, terrain, trees, everything could be handled really well by voxels. So what were some of the interesting challenges of this, and like what did I learn? A lot of the work in really optimizing a voxel cone tracing or ray tracing system in a voxel data structure is dealing with the high variability in code paths. So there's high variability both inter and intra warp workloads. So a warp of say 32 threads, typically on most NVIDIA GPUs, they execute instructions in lockstep, and so you can't really. If you have complicated control flow traversing through your loop structure, and you end up essentially just paying the cost of all code paths through the warp. And then there's also a different type of variability penalty in inter-warp workload, where if you need, on the order of, again, 16, 32-ish warps to fill out the workload of an SMX unit. And if you do not have enough warps active, you're just sort of stalling the resources. And so you really need a tight balance having enough of those active. And if you think of the typical default assignment of threads to warps, where you're doing it in a small spatial blocks, some warps that are coming over here and just hitting a surface at an aligned angle will exit early, and that's fine. They're all mostly coherent. But you have, again, this problem where I have high variability in many of these surface areas here, where you're going to have one thread that is stalling the entire SMX. It's stalling all of the workload because all the other threads and warps have exited, but it still has a significant number of voxel nodes to transit until it actually hits the surface. So that high variability, very regular workloads turns out to be very difficult. And what you end up doing, explore a number of different techniques, and the efficient techniques end up involving ways of dynamically pulling work from queues. And so you end up needing atomics. And then with using atomics, you can dynamically pull from shared queues. Every time the work unit is finished, you can just pull the next one, and that ends up being one of the limits on your performance. This trade-off between how quickly, rapidly, and efficiently I can balance workload versus the extra cost of that versus the size of the work itself. There are other techniques, but that is one of the main ones. It always ends up being some variation of using a shared fast queue structure or work stealing to balance the workload at certain choke points between different threads and different warps. And the other somewhat related lesson, and one of the ways I started to get much more interested in AI was that once you really succeed with this sort of voxel engine, you become limited by the volume of data. And so you need to invest more and more in more advanced procedural generation, or you need massive data sets that you store in the cloud. And so I became extremely interested in using neural networks to learn all these complex procedural patterns and compress the data. And around this time, I was also following, especially starting to follow some of the work coming out of Hinton's lab, where they were some of the first to start applying neural networks, running them on GPUs and rewriting them in CUDA. And of course, one example of this is AlexNet, which was one of the first, I think, real scaling successes of scaling up simpler neural network techniques on a much larger data set using GPUs and achieving a new performance breakthrough. It was very simple CUDA code. I remember looking at the code for AlexNet, and it was relatively simple compared to what I was used to when I was working with previously on terrain and octrees and everything. And I thought, I can really do better than this. I think this could be much faster. All right, so at this point in time, I was done with OnLive. This was my last exit from games. I had a bit of Bitcoin money saved, and I, at this point, was just deeply researching neural networks, reading everything I could. And then I started really focusing on this problem, narrowing down on adaptive sparsity. I'm going to explain what that means, but adaptive sparsity is this idea that it's heavily influenced, technically just a variation of the same idea that I was working with LED systems for a long time. It's the idea that in a highly efficient system, there should be a price equilibrium. And you apply that to neural networks, the cost of activating a synapse is 1 memop, let's say. And there's also some ALU, of course, but it's basically a fixed cost, like the cost of a triangle. But the value varies, and the value depends, to a first order approximation, the value depends on the magnitude of the input neuron. And so in a highly efficient, like optimized, you apply sort of LOD, the same sort of LOD theory, then I can make very fine-grained decisions around which synapses to activate based on the strength of the neuron activation, because that determines the contribution of that activating that synapse to the final result. So this is a excerpt diagram from like a patent application from like 2016 or something, a long time ago, that exploited some of the basic idea, or tries to. But you can think of it basically as like LOD at the dynamic level of detail at the neuron level. So to explain this kind of complicated diagram, on the left and the right are the exact same problem, the exact same neuron activation vector X, exact same weight matrix W. The only difference is a difference in the culling threshold, which is sort of determines our price cutoff. What is the approximation level? And so the left is using a smaller threshold, so less approximation. On the right is using a higher threshold, so a higher level approximation. And then we have on the left, on the top, then I have a graphical representation of the problem, and the bottom I have a numerical representation of the problem. So you can see here's like the 4 input neuron activation magnitudes, and here's the computed outputs, and then here's the weights showing which ones are activated or whatnot. And so the basic idea is that a really large magnitude neuron activation, a really strong input, will activate all of the weights. A medium input neuron will activate some portion of the weights, only the strongest weights, and a really weak neuron will only activate the strongest weights. That's the basic idea. And you can see the other way of thinking the core idea is that we're doing culling not in the input space of the input vector or the input matrix or input matrices. We're doing culling in the expanded product space. So for vector matrix multiplication, that's just the 2-dimensional space of the matrix itself. For matrix multiplication, that would be the 3-dimensional volume of the full expanded problem. We're going to do culling in that space, not the inputs, not the outputs. So to give you a little idea, another way of expressing the concept is that if you look at this, this input here, this neuron X3 has an activation value of 0.1. And that means that most of the computations it contributes to are going to have a very small impact on the output. So at this level here, this on the right, where we have a somewhat higher culling threshold, we're only going to evaluate one of the weights of that neuron, one of its FANAP weights, instead of all of them, as here. And you can see that results in a very small, a relatively small, not very meaningful approximation error. All right. So how does this actually work? Like, it sounds like a great idea, but if you actually apply this on a real problem, does it actually work? And so I never got to the point of really trying this on really large scale problems. So, this was back in 2015, 2016. So of course I'm going to run an MNIST, and we find yes, it does work in MNIST. The approximation error is very controllable. You get a fairly large theoretical speedup. However, then training immediately becomes the problem. The current, the sort of standard algorithms don't really work that well in this new regime because it's a very sparse, dynamic sparse regime. So you avoid there's problems with dead neurons. We developed one simple technique, which is cost regularization. The basic idea is let's just take the actual computational costs, like the number of weights that are activated dynamically, and use that as a regularization term. And one simple way of doing that is you just have a regularization term. It's not on the weight. It's not weight. It's on the weight activate. It's on the weight magnitude penalty. It's a neuron activation penalty. And so you penalize neurons that are activated very strongly because using like an L2 norm, because those are the ones, the number of weights they activate is roughly proportional to that. And that worked reasonably well. And I wish I had some of the visualizations of the resulting data, but one of the really interesting things is what the shape of solutions that were learned under a cost regularization. And one of the striking things that I remember is that the first layer on MNIST often learned neurons that only had 2 weights. 2 weights carried almost all of the information content. And that seems like really bizarre at first, but then when I think about it, you think about it a little bit more, the first layer mostly seems to do edge detection. And you can actually do edge detection with neurons that only have 2 input weights. So it figured out a way to do that. All right. So getting a bit more theoretical, there's a huge difference between the theoretical speedup and the actual speedup. Theoretical speedup is just what is the reduction in the number of weights that are loaded at different in some reasonable approximation error that we think is useful. And it really depends on the distribution of the weights and the activations. If they are normally distributed, it's only a small speed up, like on the order of 2 to 4x over regular sparsity. If they are log normally distributed, and recall the log normal distribution, most of the energy or importance is carried in a very small number of samples, and most of the elements are very small proportions. So it's very concentrated. If a very concentrated log normal distribution, you get much larger speedups. All right. Actual speedup is much harder to achieve. It's more difficult than even regular sparsity, which itself is also very challenging. There's a lot of challenges accelerating sparse neural networks on GPUs, which I'm going to get to in a little bit. But it also really depends heavily on your batching assumptions. So I'll discuss that more shortly. Around this time also, I was very interested in the brain. So I was studying the brain a lot. Here's an example of a blog post summarizing some of that. And so one of the things that I did is look at the brain itself and as sort of a data point to answer some of these questions as an example system. What are the distributions of the brain like? Are they more normal or are they more log normal for the weights and activations? What's the level of sparsity, et cetera? And so one of the interesting things is that if you actually look in the research literature on sparsity in the brain, there's a pretty interesting argument that I think first was made by Lenny. There's some interesting the sort of summary quote of it. But he basically does this principled from physics analysis of the energy consumption of spikes, maps it all out from what was known and all the known biophysics of that. And then from that, he computes a constraint on the number of spikes across the entire brain and the number of synaptic activations. And he roughly gets an estimate of less than, it's around 0.16 spikes per neuron on average. So the conclusion here is that in general, the brain is very sparse, much sparser than artificial neural networks at that time. There was a later paper that was probably more comprehensive based on actual measurement called the logodynamic brain. And what's interesting here is that they're measuring the actual distributions, firing rates, weight synaptic activations. This particular image I've captured here is just firing rates, but they found log normal distributions and everything. They found that the strength of synapses, the size of synapses, all of this was log normally distributed. But there's also some other interesting things, the local circuits. So most of the spike activity in terms of the total number of spikes, at least in the cortex and probably in other regions as well, is dominated by fast spiking interneurons. But the interneurons only project locally. So they're doing a purely local computation, which of course is less energy expensive. And the principal cells are spiking at a lower level, a lower overall rate. So they're more sparse, but those principal cells have, like the pyramid neurons, have much longer reaching axons. So in a sense, it's energy normalized, that the spiking rate is equalized under energy constraints, because the energy cost is mostly determined by the total wiring length. All right, so I want to just now map out what a log normal distribution in a cortical neuron could look like, or my understanding of what it typically maps to. You could have maybe this is a neuron that fits this log normal distribution, which seems to be prevailing. There might be one dominating weight. The dominating weight is one that if it activates, that totally determines the output of the neuron, completely overrides everything else. It's that important. One example would be there's some circuits where there's a special synapse or weight from an interneuron that attaches directly to the neuron body, and it basically multiplicity negates the output of that neuron. That would be a dominating connection. You might have 10 strong weights, 100 medium weights. I know this sounds like some sort of Christmas Carol song or something, but 1,000 weights, and then the sea of weights that really dominates the Taylor distribution is these what really should be thought of as virtual weights. And what do I mean by that? A virtual weight is one that has to exist in the brain purely for measurement purposes. It has no effect on the forward pass. These little virtual weights are sort of floating in and out of existence on relatively short time scales. And there's also other interesting research from the brain about quantal synaptic failure, which is the concept that only a small number of synaptic spikes actually transmit. Most spikes, most of the time, fail to transmit across the synapse. And that's random and stochastic. And that's because most of them are in these virtual weights. If you think about it versus an artificial neural network, in the brain, since it's a physical mapping of the virtual network to actual physical connections, for a connection to be learned or measured in the first place, to make any kind of gradient-like measurement over the importance of this weight, the utility of this weight, it has to first exist. So most weights in the brain are these sort of virtual weights that are currently being explored, but they don't actually contribute anything yet. They need several different back-propagating spikes before they're actually going to become strong enough to make a real contribution. But they have to exist before that even could happen. So with these really sparse neural networks, one of the core things is the batching assumption. I think one way to think about this, compare vector matrix multiplication to matrix multiplication. They have very different scaling properties in terms of their ALU versus memory. In particular, vector matrix multiplication does not take any advantage of excess ALU, and so it ends up being completely memory bandwidth dominated. Whereas matrix multiplication, you can basically take advantage of an ALU to memory ratio that is proportional to the size of the matrices or the block size. So today, with ALU to memory ratios in tensor cores approaching around 3 orders of magnitude, it's around 1,000 to 1, means that the ideal block matrix size is also around that size. It's around 1.024 or possibly even larger. Because those are the size of small block matrices that are balanced between their memory bandwidth and the ALU on a GPU. But this sound poses a problem. And that problem is that as a neural network designer, as a neural network architect, you are constrained to use MapMul, even in scenarios where vector-based multiplication makes more sense. And if you wanted to simulate an arbitrary circuit, like an arbitrary universal RNN, or even simulate a GPU, or simulate the brain, the obvious thing to do, not even obvious, but the correct thing to do is to use the vector matrix multiplication. matrix multiplication is a much more constrained, limited use of ALU. It's not equivalent. You could like a vector matrix multiplication system can simulate matmul, but not the other way around. Another way of expressing this is it's sort of von Neumann's curse. It's the way that our current architecture of computers is built. The entire premise is based on this segregation and discrepancy between RAM and compute. And compute is usually placed in the center of RAM, which you can see here on this GPU diagram, and it surrounds the compute. And we have this specialized circuitry just for storing information in RAM, and then we have to actually pipe that into the chip. And in modern computer architecture, the cost is mostly dominated by wire energy. It's topological. So, like flops, you have 3 orders of magnitude more flops than memory bandwidth in bytes, because the inter-wire distances inside the tensor core unit that move data around are roughly 3 orders of magnitude less total length traveled. So that's all happening deep inside the core of this GPU, and it's transmitting the same number of bits or bytes over very, very small distances. So you use less energy, you can do much more of it, you can pack much more of that into space and time. And this is just a fundamental constraint of the physics of these chips. So the brain is very, very different in that it places the compute directly on the memory. They are one, they're unified. And that's more the normal neuromorphic approach. And if I was going to make one strong principled bet on what computing paradigm will come after GPUs, it would probably be some form of neuromorphic computing. Another way of looking at this, understand this problem, is considering why batching is hard and problematic. So in modern transform architectures, you can think of them having 3 temporal scales by which information is stored and used. There are activations, the neuron activations, which store the most fast, high-frequency components of the system that are varying immediately with information flowing through the network. Then there's the KV cache, which stores information on a short and medium time scale that varies based on the input prompt. And then you finally have the frozen weights, which in most applications do not change at all once after the network is deployed. In the brain, we have activations, which are almost exactly the equivalent of neuron activations and transformers. And then we have short and medium-term plasticity, which is pretty much the direct equivalent of the KV cache. And then we have long-term weights, which are mostly the equivalent of the frozen weights in a transformer. You can think of the KV cache as equivalent to short-term weights, except they grow sort of without bound. At every time step, you're adding a fixed new amount of weights into the short-term memory, and you're not ever reusing or compressing. There are some new techniques trying to maybe move beyond transformers that are moving past that. That's currently how most transformer architecture works. And so with transformers, you're making this trade-off, which maybe not explained right here very well. It's better explained here. Transformers make the trade-off to give up recurrence in exchange for temporal batching, so you can fit the problem into the standard constraint of matmul and thereby achieve a high LU memory ratio and accelerate training dramatically. Right? That is the core reason why transformers are so successful, is they impose this design constraint in the system that allows you to take advantage of large batch sizes during training, because now you can actually use time as your batch dimension. So if you're looking at, this is the way of viewing transformers where left to right, I have time as the position in the sequence or the token position. And you can see then I can now apply that as the batch dimension in my matmul problem. And thus take advantage of high ALU to mem ratio. So, what if you want recurrence and fast inference? Well, then you are in the brain-like regime where you are completely memory bandwidth limited. You can't really take advantage of high ALU to mem ratio. So you sort of have to pick one. One, you try to achieve high throughput and get back batching and leverage high ALU to mem ratio by having some way of having an extreme number of agents or parts of the neural network that reuse all the same short-term memory and weights. That seems really difficult to do for reasons that should be mostly obvious, but I may have a slide for. No, I don't. If you think of this is the same problem that comes with transformers, why inference is slow with transformers. Because each individual instance of a transformer, as the KV cache is expanding, it is becoming different from any other transformer instance, and so it's really hard to batch them, unlike batching the weights. So if you have an inference request coming to a transformer and it has no input prompt, it's just say like the first question with a very, very short prompt, then of course you can take advantage of a large amount of batching because there's very little differentiation between that and 1,000 other requests that are similar. But the longer you fill up the KV cache, the more short or medium-term memory that particular instance has that differentiates from others, then the less you take advantage of batching. So the other approach is just to just go purely for speed and run with a batch size of 1, and then take advantage of the fact that we can use maximal sparsity to reduce the amount of memory loaded. And that is the approach that will result in the fastest possible execution speed, but not the fastest throughput. So there's sort of a fundamental trade-off here on current architecture. All right, let's get up to the present and talk about NVIDIA's market segmentation strategy. So NVIDIA used to be a gaming company until relatively recently. And you can kind of see that here, where if you go back to 2001, their gaming revenue was greater than data center revenue, or they were about on par. But then this interesting thing happened, and I guess you could sort of blame it on ChatGPT, but data center revenue just dramatically took off. It really went exponential over a short period of time. And it happened, what I think most people do not realize is it happened over a time scale which is much shorter than the time scale of large architectural plans. So it's not like NVIDIA had time to go and make an entirely new architecture for this market segment. That is not what they did. That's not what they had time to do. They took their gaming architecture and they differentiated it slightly. So on the left here, you have the architecture diagram for the SM unit on an RTX 490, the ADA architecture. And then on the right, you have the equivalent for the H100, which is of the same model family. And if you look in detail here, there are some differences. These are not exactly the same microarchitecture, of course, but they reuse a lot of the same internal technology. They're very similar. The tensor cores are very similar. There's slight differentiation. The tensor cores on the RTX 490, they made decisions that these would be used more for inference. So they have less of the higher bit width pathways accelerated to some extent. They allocated less silicon die area for higher precision pathways. You also see that the H100 variant has a lot of real estate allocated to FP64, which the consumer variant has almost no real estate allocated to that. In addition, the consumer variant has a certain fraction of the die allocated to this ray tracing core, which from my perspective is mostly kind of useless, and I kind of wish they'd never done that. I don't think it's even that useful for graphics, but whatever. They did that. But likewise, you could point out that on the enterprise variant, they're using up all this die space for FP64, which really has no meaningful impact on neural networks. But other than that, I mean, they're really similar dies. They use a lot of the same core tech. And the main difference is that the enterprise variant of the chip will have more RAM, and they use much more expensive RAM in the form of HBM. And it usually has around 2 to 2.5 the bandwidth of the equivalent consumer chip at a much higher cost, and also a larger amount of that RAM. Okay. Now, let's get to some actual benchmarks. So here, I've taken the
So I'm sorry, Jake.
this.
Do you mind if I
Yeah,
ask you something? So it's just about the previous slide before we go into benchmarks.
yeah.
You know, like one criticism I've heard of like basically GPUs were like really for graphics and they were evolved for like machine learning. And I've heard that both criticized and lauded. So, for example, I've heard it criticized because, well, like you know, like hardware vendor X might be like, well, we're just like really purely about ML and accelerating transformer performance. Therefore, we have a strategic advantage. On the other hand, I guess the benefit would be, well, you have a bunch of graphics programmers like yourself who are now, like it's sort of the same software architecture. I can take the code I wrote for gaming GPUs and now run it on server GPUs. And that's like a positive. So I figured maybe the answer like was this a good bet or not is a bit nuanced. Like obviously it was a good bet because Nvidia is one of the most important companies in the world now. But I'm sort of curious if you sort of like have like a sort of slightly different take than those two
Oh
main
yeah.
ones.
Oh yeah. No, I had strong opinions on this. Maybe I didn't express them clearly enough. Even if I was only interested in graphics, I definitely would not want a dedicated graphics logic chip. So if you go back in here, let's go way back in time. When I was working on GPUs like this, sorry, this is it's not a good representation of the actual layout of the chip, everything, but it gives you just an architectural diagram. And this is not what I wanted. I mean, this is like really specialized hardware that is optimized for its particular purpose, determined by the architects at that time. It's extremely constraining for me as a GPU programmer. I want to go wild. I'm working on things they didn't even think of. I don't want to use fixed function hardware. Are you kidding? Like this was an enormous breakthrough that they made this chip that's like very general purpose that you can use with CUDA, and it's literally just like a C++ accelerator. That's what I want. I want a chip that accelerates C++, parallel C++. That's what I want. I don't want you to make any assumptions whatsoever about what I'm going to use it for. I'm going to use it for things you've not even thought of. I'm going to think like that's the entire purpose. So these like cone tracing stuff people are doing, this doesn't use any of the dedicated graphics unit, and I'm not even like a tiny bit. This is all running on general purpose circuitry, like compiled from C++. So that's my strong opinion on that. Let's go back to these modern chips. This tensor cores, like, okay, you know, I'll use it. I don't want to. I can't. It limits me. Like I can't like run these really advanced algorithms. Like I can't run adaptive matrix multiplication on. I can't run this on a tensor core. I mean, I've tried. You get kind of close. There's some things you can do, but it's really, really difficult. It's very, very constraining. And this thing, I mean, I don't even know it's worth my time to like try to figure out what I would do with this ray tracing. I think it's just basically useless.
Interesting. But it does, yeah. Like at least for tensor cores, like what I'm hearing you say is that like fundamentally, it's sort of a very useful accelerator, but it's not like a useful research accelerator tool. And so, like, and kind of like back to your analogy of like, I want fast parallel C++. Like a tensor core is not that, right? And so,
No,
yeah, I see.
it's very
Okay.
I think it makes sense they put it on the chip. They were otherwise they'd face pressure from. There's a trade-off that they have to make. They have to make this trade-off between accelerating known algorithms as they are right now, and then also having general purpose circuitry that can accelerate future unknown algorithms. And they always make that trade-off. And what I see looking at this die right here is that they dedicate almost half of the core to accelerating known dense MATLAB algorithms. It's not necessarily, and it's not that bad. Like I would argue, push back a bit, maybe it should be a bit more than that. But at the end of the day, the sparse algorithms are mostly limited by memory bandwidth. So in fact, like I don't really even care about much of this stuff that much. Like I would want more of these load units. I'd want more shared memory, faster bandwidth for shared memory, much faster global memory bandwidth. That's what I would care about. If they're going to have dedicated logic on this, if I was making a chip for the type of algorithms I'm interested in, the dedicated logic would focus much more on accelerating compression, decompression of weights that are compressed in advanced formats. That's kind of what happened with graphics. When graphics algorithms got really sophisticated, you end up just becoming memory bandwidth bound. And the thing that you end up wanting is a really optimized compression decompression in the hardware level. So that's what happened with textures, for example. They moved a lot of the compression, decompression on the chip so that you became less memory bandwidth on your one of the core things that is memory intensive, the textures. And I can see that's an interesting direction that you can go, and that would work much better for the type of algorithms I'm interested in. If they had some of the dedicated logic for really compression and decompression of weights encoded in various complex formats.
So yeah, I think that answers the question. So we should I'll let you get back to the flow.
Yes, but anyway, like the thing I was trying to illustrate this is like the time scale here is too short. They did not have enough time to go in and like do much. You know, they kind of threw these tensor cores on their chips. Basically, what they did. All right, so here's I think an interesting benchmark across different types of precisions, going from 32 to 16 to one of the main 8-bit float modes. And then on the left we have this matrix size. I've only done square matrices here. I didn't do rectangle or anything other more interesting. But you can get the general trend. I'm only comparing 2 GPU models here that are the same sort of rough architectural family. One is the differentiated H100, one is the 490 main top line consumer. And what's interesting is that the 490 mostly dominates a bit, but not by a huge amount. It's a bit faster for if you're doing only 32-bit, pretty much across the board. And then for float 16 and float 8, the H100 has an advantage that grows basically with the size of the problem, the size of the rectangular block you're using. So as you use larger batches and larger rectangular blocks, they're more and more dense and regular. The acceleration grows up to, let's say, in the maximal case, up to a 4x, about a 4x difference for this one mode of float 16. One little note on this particular mode of float 16 is that this is a mode that's intentionally not fully accelerated. There is a variant of this that is faster on the consumer GPU, but it's the difference between float 16 inputs and float 32 accumulation versus float 16 inputs and float 16 accumulation. And the default pathway in PyTorch assumes the 32-bit mode, I believe, and uses that pathway, which is slower on the consumer GPUs. Anyway, I think that also applies to the 8-bit modes. But if you put it into dollars, like flops per dollar, the 490 is always dominant across everything. It's just a question of whether it's dominant only by a factor of 3x or 2x or something. In some case, 10x. But so really, the H100s are optimized for the current structure of neural networks, where especially transformers, where you can take advantage of or use really large, dense, roughly square matmos. But the more you go out of that paradigm, the less advantage they have. And they have really no advantage in regular compute. If anything, they're a bit slower. Okay, I'm going to pause here if there's any questions on this, or maybe not.
Not a question, but maybe more of a comment. Like, it reminds me of like sort of this like NASCAR analogy, where like because like if you need to only turn to the left, then you can tilt your suspension, but like if you drive anywhere else, like you're not going to have a particularly good car. And I think it's kind of interesting, like I hadn't considered, like, because typically indeed when people compare consumer GPUs, they'll sort of say, oh, like how fast is a transformer? But what you're saying is really, if the architectures are like a bit irregular, then have fun, and then a 4090 will be significantly cheaper for you to work with. That's an interesting take. Okay, yeah, more of a comment, but yeah, I
well, even if you're running a regular transformer, using everything off the shelf, the 490 is still going to dominate in dollar costs, assuming you can fit it into RAM and everything. There's no point in which the H400 dominates economically. It's completely dominated by the 490.
Interesting, I see.
But it does depend on the nature of your problem. Like the H100 strength is going to be in more standard, regular, large matrix, very regular, very dense. And also, I should point out, at some point I should go in and like actually rewrite this in lower level CUDA that uses the lower precision accumulation. I don't know how much difference that would make, but it might make up to a 2x difference for the 490. Yeah, like to go to your analogy, like if I was writing something that used ray tracing code, I mean, and it's specifically structured for the ray tracing API and assumptions they make for this hardware. And that, that's like the H100 would score very low in there because it would have to emulate that with its general purpose circuitry. But obviously that's not interesting. So what's interesting about H100 is the larger, fatter tensor core for certain modes and pathways. It has a higher performance, like usually like a 2, sometimes 4x faster pathway per SM, if you can take advantage of those specific modes. But the 490s are, I think, almost intentionally by NVIDIA, like less exposed or optimized. So you really have to write your own kernels to use the 60-bit, take advantage of the 60-bit accumulation and whatnot. And most people have not done that yet. So this does not even, I think, use those pathways.
And so at least for these benchmarks, like were these with CUDA, Trident, PyTorch, like?
Oh, this is PyTorch. This is just PyTorch.
Okay.
This is not my own optimized field. It's just off-the-shelf PyTorch. But some recent version of PyTorch supported this mode. There was some little thing with that, but yeah, this is just off-the-shelf PyTorch.
Got it. Okay.
All right. Okay. So this is going to take some more explanation, but one of the benchmarks I run as like a micro benchmark for a lot of the sparsity stuff I'm interested in is I'm really interested in shared memory performance, because that's one of the things that's global memory performance is usually just what you see in the tin. So for example, like the RTX 490 claims 1 terabyte per second of bandwidth, and that is really what you get. Like if you actually measure it, start using in kernels and profiling it, like maybe you get 90% of that or something. That's not that hard to get 90% of it. What's much more mysterious is what is the shared memory performance. I'd say also L2 memory bandwidth performance is also somewhat mysterious, but shared memory bandwidth performance is very mysterious. And by that I mean it's complicated. It depends a lot on the structure of how coalesced you are, what you're doing, what the exact pathway is, all this stuff. So it's one of the more interesting things to measure. So on the left is just the measurement in terms of number of ops, but they're pretty much all 4-byte ops. They're all 32-bit ops. So it's more interesting to look at these 4 columns over here. And this column, hopefully you can see this, but actually these 2 are both coalesced atomic operations. The one right here you can mostly ignore. It is NVIDIA has like a coalesced atomic for, I think, FP16. That's what this is. And this is just showing that no, the FP16 stuff is still really slow and probably not really that useful. This is integer. And then you have one over here, which is non-atomic to compare to like just general shared memory that's not using atomic operations. And then this is random scattered atomic. So if you're not really paying any attention to coalescing, and you're sort of breaking the rules, and you're just doing random writes, random atomic operations scattered across memory. And what you see is across, and here's the different GPU models. I've not matched them up, so I'd be interested to see what people's predictions are. But 2 of these rows are from RTX 490 across different versions of CUDA. And there's one row it's RTX 590 and one row is the H100 NVL, which I think is the highest performant variant of the H100. And one thing that's interesting before like showing which achieves what is that the random scatter performance is always, of course, slower, usually by a factor of 3, sometimes 4, but that ratio does vary somewhat significantly. But they're all kind of around the same speed. Like none really has a huge advantage. The non-atomic shared memory bandwidth is almost the same ballpark, except this top row GPU model, which is maybe 50% lower. And then the coalesce, the best case for atomics, is also somewhat interesting pattern, like somewhat similar pattern, but does not actually match up the non-atomic. So you have this one GPU, which is like whatever this one is. The coalesce atomics and non-atomics are similar, but the coalesce atomics is actually faster, which is kind of weird. And then this GPU, the coalesce atomics are about a little bit less than half the speed of the non-atomic, just regular shared memory access. All right. Does anyone want to make a guess of like which of these map to which GPUs? I know. It seems like totally random. I know. So, okay. All right. So the top one actually was the H100. The middle 2 of the 490s. The bottom one's the 590. And unfortunately, I did not have enough time to really figure out why CUDA 12.8 is slower with this benchmark. I wish I had more time to actually debug that, but I just tried this in the 590 like the other day. I didn't have enough time to actually figure it out. So I also put in the benchmark of the 490 and the 12 with CUDA 12.8, because it does turn out indeed that there's something going on with CUDA 12.8 where it's slower for some reason. I've not figured out. I've not done the analysis of like the lower level disassembly to see what's going on. But if you compare the H100 and the 490, both on the older version of CUDA that has no issue, they're roughly comparable across the board, except the 490 is faster for non-atomics in this benchmark, which is interesting. But for coalesced atomics, they're about the same speed. And the 490 is somewhat stronger in random scattered atomics. So this is interesting. That's an example of it. It just goes to show that the H100 is somewhat optimized for these large matrix operations and really not much else. And to some extent, they've made some trade-offs where they've lost some performance versus the consumer GPU on more general code. All right. Any questions on this one or no?
No, we can keep going.
Say what?
We can keep going.
Okay. So one of the things interesting, now this is just a radical hypothesis, but if you come back to the whole Win AGI thing and Moore's law and scaling hypothesis, there is now this massive investment of resources in scaling up, basically scaling up AlexNet. And when I say scaling up AlexNet, I know that there's been architectural improvements since then. Like transformers are, a general improvement. But what I mean by that is like scaling up these dense neural networks and taking the type of neural network you could run on one GPU and then running it on ever larger clusters, where the clusters are all densely interconnected to essentially function as a single massive GPU. That's the current scaling paradigm. I think in a nutshell that mostly captures what's going on. And we're now getting up into the regime of getting up into 1e to the 26 dense flops for a training run. I don't think they really spent $1 billion on the 4.5 training run, but so I think there was discounts and some performance improvements, but it could have been up that high. And even if it wasn't, there certainly are $1 billion training runs that are probably currently in the works. And I think it's crazy is to consider, based on the stuff I was showing earlier, on the known sort of parameters of the brain, there's only about 1 to the 14th synapses. And if we know that on average they activate or fire at a rate of about 0.1 hertz, and we know that humans can become highly intelligent and productive and have enough knowledge to do useful things in the world after only 33 years, which conveniently is 1 in 9 seconds. And then you get an estimate of 1 to the 22 ops, which is 4 orders of magnitude less compute cost than current large training runs. So I do believe we're in a situation where it's possible that dramatically better algorithms exist that have just not been discovered yet. I think I have some sense of what they are, but it's just going to be a lot of work in terms of figuring out exactly how to restructure all of our training algorithms. But I do think it's even possible on current hardware. So that's a very interesting, I know, somewhat radical premise, but I think the evidence for it is reasonably compelling. And so it's one of the things I'm interested in pursuing. And yeah, that's it. That's my last slide.
Sweet. Thank you, Jake. I guess, yeah, if folks have any questions to Jake, now would be a good time. I guess I'll start off like with my own. Like it sounds like for the vast majority of your own personal like research, like it sounds like you just end up effectively using consumer GPUs. And so like and I guess like really, I guess if you could ask something of NVIDIA to just like basically improve something in their enterprise GPUs to make like your kind of research more feasible, like any sparsity research, is there like any concrete ask you'd make, or you just think like a general purpose machine like the consumer GPUs is like more than sufficient?
Yeah, it's mostly general purpose machine. I do think it. My main ask would be not to over specialize on current algorithms. That would be the main ask. If there is anything that should be specialized, that I'm interested in to be maybe some low level instructions to accelerate some of the compression decompression operations. And then really at the architectural, the hardware level, the one interesting direction, if you really want to maybe just go in a more radical direction, it's to, let's see if I can explain okay. So the next thing I think would be interesting going the more normal approach is splitting up this large chip into smaller chiplets that are directly connected to a memory stack at a much higher speed. And so moving to a regime where you have a much higher total global memory bandwidth for the same amount of RAM. That could be interesting. That would accelerate type of neural networks I think are interesting. But then beyond that,
so this is like a graph core like approach basically, where you just have like
I'm tempted to just look up graph cores. Let's see if I can find architecture. I didn't think the graph core did that. I did not think that they had. Did they? Because it's kind of sad because I thought the graph core was sort of dead. But
yeah, like I think it might have been in the US, but like you can click on that first picture.
Okay, so
yeah.
This just looks like to me like I don't know. This just looks like a variation of GPU chip. It's not really like going in a normorphic direction. I think there maybe are some startups that are doing more what I'm talking about, but like really what I'm talking about is like moving the compute much closer to the RAM, and not using SRAM. Like everyone, there's all these startups that start. I think maybe GraphCore's in that category where they were trying to just put all the weights in SRAM. That's not what I'm talking about. That's not. We do need like a lot of RAM. I think that's pretty clear, especially with sparse neural networks, because you're just not compute limited. You're constrained by RAM and RAM bandwidth. The RAM bandwidth determines your speed, and the RAM determines your size. And you want both. You want large neural networks that are fast. So you want a lot of RAM, and you want it to be very fast. You don't need that much compute, but you need to put that compute really close to the RAM. And current GPUs are limited because they have a huge die that is surrounded by RAM. So they have to pull all the weights, have to transmit this long distance to get into the cores. And that's the core problem. And you can't just make a huge. So there's other approach like Cerebras. I think that's also somewhat a wrong approach. Cerebras wafer die. I'm trying to see if I can pull it up real quick. But like Cerebras put in this approach of just putting everything on one huge, massive wafer scale die, and that doesn't really explain it.
But I also think they have challenges around it being general purpose, because I think they have to rely on a very clever compiler. Is my suspicion. It's not like quite.
Yeah, but it's not I think the core problem is not that. The core that I think can be overcome. The core problem is that they went with SRAM, and SRAM is just way too expensive. Yeah.
Sorry. So makes sense. Yeah. Like I do want to make sure we get to other questions from chat. Like so Alex is asking, like, isn't this sort of an apples to oranges comparison though? Like in the sense that LLMs condense a lot more raw info than any one person, while human brains in theory generalize much better. I think this was a point regarding like one of the last slides that you had. Yes, probably this one. Yes.
Yeah, like this graph does not show it very well. I wish I had a slide for it, but I think that intelligence is proportional to net training compute is like roughly correct. But really, you could think of that as like there's two axes. So the net training compute is the product of one axis is the total training time, the total training data size. And the other axis is the amount of compute spent per unit of time or unit of data point. And if you look at it that way, current LLMs are in a very different area of that map. They're over in the extreme of very large amount of training set. Like they're if you think of it as like a experience of a lifetime, they have the equivalent of hundreds of human lifetimes, but they're much smaller, and so they're applying less compute per time step. And what does that mean? Well, it means they probably learn almost, not that's just probably, it seems pretty clear they learn more slowly per time step, because the speed of learning per time step is determined by the size of the model, or how much compute it can spend to do inference per time step. So the human brain is in a regime where it's very, very large in comparison, and it's applying a very large amount of compute to learn more rapidly per time step, because it's much slower and it has so much less data and experience. I think that roughly describes. So current LLMs are superhuman and overly performant. They're doing really well in regimes that are mostly knowledge limited, because they've been able to actually read the entirety of the internet, which a human would never be able to do. A human might experience 10 billion tokens, let's say, 1 billion seconds, 10 tokens per second. And these models are currently being trained on up to, I think they're well into the trillions of tokens. So
yeah,
it's a different regime.
So I still see 3 more questions in chat. So like one natural one, like I guess I think I know the answer to this one, but like, do you want to dish out any flame towards consumer AMD cards? And like, how come you didn't talk about them during this talk?
You go way back in time. It's been a long time since I did any development on an ATI card. It was all the way back and working the Xbox 360. And I will say that was a joy to work with. I really liked that card. I mean, compared to NVIDIA's thing on the PlayStation 3, it was way better. But that was a long time ago. And I've not been impressed with a lot of their work since. I think it'd be great for competition. There's one scenario here. I wish that AMD would like ignore this green part of the chart and focus more on the gaming segment, and keep pressure on NVIDIA to make sure. Yeah, because NVIDIA now, financially, they could just give up gaming. They could just give it up. They don't have to produce consumer GPUs, and that would suck. But I'd hope that AMD would fill in the gap there.
I guess let's leave this another question in chat is like, what do you think of NVIDIA's new Digits project?
I've heard of that. I've not looked into it a lot. Is that like a high RAM personal machine thing?
Yeah, like it's a crazy unified memory budget, so you can just do chunky LLM inference at home. Yeah, that's the one.
Yeah, I guess I didn't look at like how much RAM. Oh, it must have a lot of RAM. So 120 gigabytes of RAM, that's pretty good. That's like 4 RTX 590s. What's the cost?
It's talk to a salesperson, it seems. So that's the cost.
Let's see if the internet knows. Wait, what? Only $3,000? I am interested in this now. If it's only $3,000, I mean, because it's hard to get a 590 for that price. Huh. This is interesting. I need to look more into this. I did not realize it was that cheap. If that really has 128 gigabytes of video RAM for $3,000, that's a pretty good deal. So it's interesting. Huh.
I mean, I think when they're out, like I also feel like my gaming PC should sort of be a different machine for my ML PC. But yeah, so I guess like maybe the last question we can cover in chat is from Daniel. So I think you already answered this, but like, do you see the balance shifting between traditional rasterization to neural rendering, particularly for real-time games? I think you spent a good amount of time bashing on the RT tensor cores, so my suspicion is, yeah, I'm curious to hear your take again.
Yeah. I mean, it's not that I'm currently making a game, but even way back when I was last working on rendering engines, there's no rasterization involved in the rendering engines I was working on 10, 12 years ago. And if I was making one now, no, I would not use rasterization. I think I have a shot here from Unreal Engine 5, and they are still using rasterization. But I remember like reading some explanation where they felt like they had to explain why they were not using ray tracing and voxels and stuff. But yeah, I would not use rasterization. Mostly just because if I was making a game today, it's so much easier to unify everything like voxels are the equivalent of image representation in 3D, and they just make it easier to integrate things. I would be doing neural generation of everything. So that would be the main driving force. Using neural networks to generate all the data, animate everything, etc. Really, though, the only part that's not just a neural network would be the sort of prior that I would probably want to structure things in some sort of hierarchical data structure like a voxel tree.
All right. Well, I think, Jake, this might be a good time to call. I want to say thank you already because I'm seeing someone like there's Alex from the Exo team that like thought like this presentation was really cool and they might talk more. So I think we're hoping to hopefully you help us kickstart more people thinking about like local general compute. So I'm seeing like people seem to really like chat. I think you have a friend in chat, Carl J. Rizzo Jr. It's Jolly, who seems to be really excited to see you. So yeah, lots of thank yous and thank you, Jake. I guess if people want to talk to you more, where do you hang out? Like, where can people ask you more questions in general?
I mean, you can come to the BAPCI Discord, and I sometimes chat there. That's one way. Yeah, you shoot me an email or our Discord. Those are some of the main things that I will respond to, I think.
Okay, excellent. Well, thank you, Jake. Hopefully we'll see you soon. And thanks again for an excellent talk. It was like quite eye-opening for me. So thank you for giving us that journey.
Thank you. It was a pleasure. And I feel like I learned a bit too. I need to look into digits more. It's more interesting than I thought first. All right. Have a good one.
Yeah, let me end the stream.